Welcome to another lecture on W211. Previously, we have discussed those circuits that contains only the resistance in them. In today's class, we shall start with the concept of the energy storage elements, and we will discuss some of the two very basic type of energy storage elements which are known as the inductor and the capacitor. So let us start with with our topic. So far, we have studied the circuits that contains only the resistance and the DC sources. The use of resistances in a circuit makes them a static circuit because the resistances are not capable of storing any kind of energy. The resistances only dissipate power, which is actually a non-reversible process, and therefore these devices are not capable of supplying the energy, and neither they are able to store the energy, and therefore the circuits that contain only the resistances are known as the static networks. There are certain elements that are able to store the energy and are known as the energy storage elements. So in this lecture we shall start with the concept of the energy storage elements, and we will see what are the different behaviors of energy storage element. So let us start. The circuits with only resistances if an element that can store energy is placed in a circuit, then that circuit is called is called a dynamic circuit, right? Now the dynamic circuits contains energy storage elements, and the instantaneous values of the voltage and the current in those circuits depends not only on the present value, but they also depend on what is the previously stored amount of voltage, or what is the previously flowing current through that particular circuit. So in a dynamic circuit, the instantaneous voltages and current depends on the previously previous values of voltage and the current, right? So there are two basic types of energy storage elements. One is known as an inductor, and the other one is known as a capacitor, right? So we shall study two basic types. There are two basic energy storage elements. The one is known as the inductor, and the other one is known as the capacitor, right? Now whenever we have the energy storage elements in a given circuit, then the circuit becomes complex, because the mathematical treatment of those of that particular circuit contains not only the simple mathematical equations, but rather we shall see the integration and the differentiation in those circuits as well. So the use of integration and differentiation in a given circuit, because of the presence of these two, because of any energy storage elements, makes the circuit complex in getting the solution. So therefore the dynamic circuits are considered difficult in solution compared to the static circuits. Both of them requires some differential equations for the solution. In addition to that, because of the concept of the energy storage in these two elements, we shall see that the circuit contains the transient part as well as a steady state part. So the overall solution of circuits containing L and C has a transient and a steady state part. And we shall see that in any stable circuit, the transient part should vanish out with the passage of time, and thereafter the circuit should come into a steady state circuit. Or most of the time when we do not have any dependent source connected in a given circuit, then the circuit automatically comes into a steady state condition after a few time. That detail we shall see in the upcoming lectures. In today's lecture, we are only we shall only discuss the properties of inductor and the capacitor with a circuit point of view. That is, we shall be only limiting our discussion to the voltage and the current relationship between in these two elements, right? So we shall be focusing only on the current voltage characteristics of inductor and the capacitor. However, we shall slightly look into the physics that is involved in the designing of the capacitor as well as in the designing of an inductor. So let us start with the first particular element, which is known as the inductor, and thereafter we shall move on to the capacitor as well. Inductor has a little bit of story involved in it because the physics actually progressed a lot during the 1800s and during the 19th century and during the 20th century. So starting from the 19th century, early 1800s, right, there was a discovery by Oersted. His name was Oersted. He discovered that a current creates a magnetic field. Oersted discovered that a current carrying conductor produces the magnetic field. Later on, the Ampere discovered that the current which actually generates this magnetic field is actually, they have a proportional relationship between them. So if the current is changing with time, then the magnetic field also changes in time, and that induces the voltage in the nearby circuit. Thus we come to know that if the current is changing with time, then this magnetic field also changes with time, and it will induce the voltage in the nearby circuit, right? So the voltage that is produced is actually because of the time rate of change of the current that is flowing through that conductor, which is producing that magnetic field. And therefore it was stated that this voltage V is proportional to the time rate of change of the current di over dt, and this can be expressed as V is equal to L di over dt, where this L is the constant of proportionality and is known as the inductance. Now the value of this L, if we say that this is equation number 1, then this value of L depends on a lot of factors, right? It depends on the shape of the core or over which the winding is wounded. Then it depends on the total meter of conductor which is used to make that particular coil. It also depends on the number of turns. Rather, it depends on the square of the number of turns which are wounded on that particular coil. So we can say that this inductance L is equal to mu n square A over L, where this A represents the area of the core. Rather, it is actually the cross sectional area of the core in meter square, and then we have this length L, length of the conductor in meter. Also we have this N, this which shows the number of turns on the the wire is wound across that shape of the core, turns on the core. And this mu, it is the magnetic property of the material with which the core is actually developed. So mu is the magnetic property of the core and is known as permeability. Now, because depending on, there are different shapes of cores that are possible, we may have a circular shape, right, or which we can have, you know, this type of inductor. We also make an inductor on this square type of core, and therefore the area depends on the shape of the core, right. Notice that the inductor is not a commercially off the shelf available device. For most of the applications, the value of the inductor is dependent on a lot of different factors, and therefore the designer has to design the inductor based on his or her own requirements. But that is not the scope for this linear circuit analysis course. The design of magnetics is an integral part of your advanced course in power electronics, where we develop the different kind of inductors for the DC to DC buck converter, the boost converters, and for the filtration process, which is usually involved in a grid tied inverter systems. But for now, here on, we are only interested in knowing that how inductance behave when it is present in a given circuit, what is the voltage current relationship, and how we actually use the inductance and the capacitance, and how we actually utilize the inductance in understanding the basic concepts of circuit analysis. So the circuit symbol here, because it is not possible to draw these type of codes every time we draw a given circuit. Therefore the circuit symbol of inductance or inductor, it is something like this, where we will follow this passive sign convention, and we have the current which is entering from the positive side, whatever side the current is entering, that is considered the positive across this particular inductor. Also, the symbol of this inductor represents an ideal inductor over which we actually try to express a real device, right. So in an ideal inductor, we do not have any resistance which is involved in the coils which is used to wind this particular core, right. So we do not incorporate the resistance here, rather we describe this as an ideal device. So this particular circuit symbol of an inductor, it actually represents the ideal device. It represents the ideal device, right. Also, the unit of inductance L, the unit of inductance is called Henry, which is named after a very famous physicist. So it is usually written as Henry, and the symbol is this H, right. So now that we do know that we have developed this equation number 1, let us analyze in detail the relationship between the voltage and the current in an inductor. Remember that this equation, which seems like a very
small equation contains a lot of information within. So let me write this particular equation. So we have V of L is equal to of T is equal to L di over dt. This equation contains a lot of information, and it provides us very important points with respect to the use of the inductor. For example, the first thing here is that this equation, it represents the voltage across inductance as a function of current, right? So this is the although we can have another relation as well that we will see shortly. This per current equation VL of t is equal to L dit over dt, where this V L of t and di of t represents the time varying voltage across the inductor and the current through that inductor. The first thing that is available from this particular equation is that the time rate of change of current di over dt is very important for the voltage across an inductor, right? So if there is no change in the current such that the di over dt is equal to 0 and that the current is actually a constant, then the voltage across the inductor is equal to 0, and hence the inductor actually behaves like a short circuit path. So if there is no change in the current, that is di over dt is equal to 0, then VL is also equal to 0, which means that the inductor is a short circuit for all the DC circuits, right? So inductor is actually a short circuit for all the DC circuits. This is the very first thing that comes out of this very important equation of the inductor. The second thing here is that if the current through an inductor is disconnected or is abruptly changed abruptly through disconnection or whatever it is, then inductor do not permit to do this, right? This means that if we want to make this di over dt, if we want to make it infinite, then certainly we want to have this Vt of infinite as well, which means that for any given circuit, if we try to disconnect the inductor and if we try to abruptly stop the current, then the inductor shall require to have infinite voltages, which is not a real world phenomena, and therefore inductor opposes sudden change in the current. So what will happen if we suddenly try to disconnect the inductor? It happens that the voltage will go dangerously high, and that can lead to the device failure. you will learn in the advanced classes that this phenomena, if we can control the amount of current, then this phenomena is very useful because it is used in the vehicle ignition systems. Personal motor most of the times, for example, in the DC to DC converters and in power electronics, doing so means that the voltage spike will eventually damage one of the semiconductor devices which are connected in that given circuit. Another aspect of this particular thing is that any abrupt change in the inductor current implies that an abrupt change in the stored energy, and this abrupt change in the energy which is stored in that particular inductor requires infinite power, which is not possible in real world. So therefore it is always imperative to devise a mechanism that prevents the sudden disconnection or sudden change of current through an inductor, right? So you will see in the later classes that these dangerously high voltages are the real enemies of the power electronic switches and the semiconductor switches which are connected in a given circuit. For example, we in a DC to DC converter. In order to prevent this phenomena from happening, the pole of a switch is always connected with this with the inductor, because inductor do not allow sudden change in current, and we have to we inductor is never to be open circuited. And to avoid that, the pole of a given switch, for example, we have a switch here, this is the throw and this is the pole. For instance, we have a given circuit here, and we want to actually, let us say that this is throw number 1 and this is throw number 2, and we have an inductive circuit here. So you should notice here that this pole is always connected in series with this inductor, right? Because inductor is never to be open circuited, because of the reasons that if you open circuit an inductor, then this di of dt will become equal to infinity, and that infinity requires to have the voltage across the inductor also equal to infinity, which means that the dangerously high amount of currents will flow through the given circuit, and that can lead to the failure of the devices. Notice here that we do not have these type of switches in an electronic circuit. Most of the time, rather all the time, we have the power electronic circuits that works as these switches, and they actually create the topologies in which the switches act as a single pole double throw switches or single pole single throw switches. However, to make these devices work within the safe limits without exceeding the voltage limits of these devices, it is always imperative to connect this pole always with the inductor, so that the inductor never becomes open circuited. Let us visualize this equation through one numerical and see what happens. So let us say we have, for an inductance L is equal to 3 Henry, we have this type of a current which is flowing. Let me draw the current here. Let us say we have, this is I of t, this is t. Let us say this is -1, this is 0, then we have 1, and then we have 2. Let us draw the voltage waveform here. So this is t. Now if you notice here that the voltage VL is equal to L di over dt. Now this di over dt, if this is equal to 1, then this di over dt for this particular circuit for this particular circuit, di over dt, which is the slope of this particular rising current, it is equal to 1. It is equal to 1 ampere per second. So consequently, the voltage VL will have a value that is equal to 3 times the derivative of this current function. So derivating it gives us a straight value, and that is equal to 3 volt, right? Notice here, right after this 0 instant, the current is constant, and therefore the derivative of a constant is equal to 0, and therefore the voltage shall have a 0 value after t exceeds 0. Another important point here is that if you notice that the area here, which is the area under this curve for this voltage, 3 volt, 3 volt second, and this is the area under the voltage V. Also notice here that for a constant current, voltage is equal to 0, and that is what we have discussed previously, that an inductor shall have a behavior of a short circuit if the current is not changing with the time. So for all the DC circuits, the inductor is actually a short circuit path. Let us alter this particular numerical a little bit. I shall only draw the current waveform here, and let us say that we have the same shape of current I of t, and we have, instead of having it at -1, now it is at -0.1, and this is equal to 1. So the slope of this current here, this di over dt, for this particular slope is, it is equal to 10 ampere per second, right? Notice here that if you are having some confusion about finding the slope of this circuit, then the slope of this circuit can easily be calculated using this particular expression, x minus x1 over y minus y1, that is equal to x2 minus x1 over y2 minus y1. So this gives you the slope of the current, and that is equal to 10 ampere per second. Now if I draw the voltage waveform, then we have the voltage will become equal to 30 volt if this v of t and this is t, it shall have a value 0 after time t, after the current becomes constant. Notice here that as we have decreased the time instant that is required for the current to rise from 0 value to its final value of 1, the voltage has drastically increased, which means that if I further try to decrease this amount of time, or if I try to increase this time rate of change of the current, then the voltage shall go higher and higher, and at some instant, if I want to have a current having an abrupt change here, that requires infinite amount of voltage, which means that the device will lead to the failure, because infinite voltage requires infinite power, which is not a real world phenomena. With this in mind, let us use that this particular equation, V L of t is equal to L di over dt. Now if I integrate this thing, if I integrate this equation, then I have I L of t is equal to 1 over L minus infinity to t naught V of t dt plus 1 over L starting from t naught to t. This is V of t dt. In here, this particular thing is not known, and it's generally it is not known. However, this particular part is known as the initial current of initial current of the inductor, or initial current flowing through the inductor, wherever this part is known as the instantaneous part, which is happening with the passage of time. So IL of t, this particular expression gives us I of t naught plus 1 over L t naught to t v of t into dt, and this gives us the expression for the voltage and the current. However, this particular equation reveals that to find out the current flowing through an inductor, the previous current which is flowing through the inductor is very important, and that is known as the initial condition of an inductor. So this initial condition is the previously flowing current, which is the current which is flowing in the circuit prior to the switching of that given circuit, and these things will be wrinkled out as we will progress with the first order circuits and with the second order circuits. As far as the energy is concerned through an inductor, energy is concerned, let us talk about the energy storage here as well. For an inductor, we know that the energy is the integration of power over a given period of time. Since P is equal to V into I, so that is equal to Li di over dt. So if I integrate this power, if I integrate the power over time, then that gives me half L Li square, right? This is the third expression for the inductor. That is that an inductor, we have the power, the energy is equal to energy W is equal to half Li square. This means that the inductor stores energy only when there is a current flowing through the inductor. If there is no current flowing through an inductor cannot store energy. So for the storage of energy, this I is very important. No matter what the direction of the current is, it always stores energy whenever there is a current flowing through it, right? If you see here, since the energy here, this energy here, it cannot change instantaneously, because instantaneous change in energy requires infinite power, which is not a real world phenomena. Therefore, the energy cannot change instantaneously. This implies that the current through an inductor cannot change instantaneously as well. So this is a phenomena which is related with the amount of energy which is stored in this given inductor, and that we have discussed a little bit earlier. And this implies that the current through an inductor also cannot change instantaneously. So what we can say here, that for any given inductor, I0 negative is always equal to the I0 positive, which means that if at any given hypothetical time, let us say t is equal to 0 is the time at which we create some sort of disturbance, or we connect a circuit, or we disconnect a circuit or some element in a given circuit, then the current which was previously flowing just before that particular instant t is equal to 0, that current I0 naught shall have the value equal to the I0 positive, which is just after the time when we made any disturbance in a given circuit. So I0 negative is the time just before the disturbance in an inductive circuit, and this is just after the time just after the disturbance in the inductive circuit, right? So inductance, if we know what is the amount of current flowing through an inductor, then we do know what is the amount of current flowing just after we make any change in the given circuit. For example, let us say we have in this given circuit, we have an inductance and we have a resistance here, right? Let us say that we have 1 ampere of current that was flowing through this particular inductance. This is a switch. At time t is equal to 0, I move this switch from position number 1 to position number 2. Now prior to this switch at time t is equal to 0, the I 0 negative which was flowing through this inductance I 0 negative, that was 1 ampere. Now right after instantaneously, then when I close this switch from position number 1 to position number 2, then the property based on this equation number 3 reveals that this I 0 positive shall also be equal to 1 ampere, because that is the property of an inductor. So it will be the discussion on the first order circuits, that what happens if after the time elapses, what is the behavior of a given circuit. We shall see it in the later classes. Here for this particular circuit, my emphasis is to only describe you that the current through an inductor cannot change instantaneously. So the whatever the value it is having before any disturbance in a given circuit, it will try to retain that particular value for a very small period of time, and that is known as I 0 positive. Next we want to see how can we actually simplify a circuit containing the inductor, right? So just like the resistances, we have the series and parallel combinations available for an inductor, and based on those combinations we can squeeze a circuit, and we can actually equate a circuit using only the single value of the inductance. Let me draw a given circuit. Let us say we have this is V of S, and this is L1. Let us say this is L2, and this is L3. Now because we have the inductances available, so let us say we have this voltage VL1 here, this is VL2, and this is VL3, and here we have some current IS flowing here. Now if I apply the KVL in this whole loop, then Vs is equal to VL1 plus VL2 plus VL3, and that is equal to L dis over dt. With respect to time, let us for the sake of simplicity, let us just write it as dis over dt. This is L1, then we have L2 di over dt, then we have L3 di over dt, and this means that the L equivalent is actually the sum of L1 plus L2 plus L3, because the same amount of current is flowing through all of these elements owing to the Kirchhoff's current law. And therefore this reveals that if the inductances are connected in series, they are treated in a similar way like we treated the resistances. So that is just a simple sum up of all the values of the resistances, and that gives you the equivalent value of the resistance. So for n number of for n number of inductances, we have L equivalent is equal to L1 plus L2 plus up to so on, and that is equal to L of, and this can be expressed as this particular, and this is equal to the L equivalent here. And these two circuits are essentially the equivalent circuit, because they are based on the principles of the linear circuit analysis. If we have inductances connected in parallel, for example, let us say we have the inductances available here, and we have, let us say these are 3 1, this is L1, this is L2, and this is L3. Then we have to apply the Kirchhoff's current law here. So we have the current IS flowing into this particular node, and it is dividing into IL1, and then we have IL2, and then we have the IL3. So if we apply the Kirchhoff's current law here, then it reveals that this IS is equal to IL1 plus IL2 plus IL3, and if we apply the expression for the current, that is equal to that gives me a value equal to 1 over L1 plus 1 over L2 plus 1 over L3, and thereafter we have the rest of the equation that contains the initial current flowing through the inductances as well as the integral part. So here we have this L equivalent is actually behaving very similar. It is behaving exactly the same way the resistances behave. So for if we have two inductances connected, so for two inductances, for two inductors, L equivalent is equal to L1 L2 divided by L1 plus L1 plus L2. So this is how we can actually simplify a given circuit based only on the value of the inductance. Let us move ahead. Let us move ahead and see the second type of the energy storage element, which is known as the capacitor. Capacitor consists of two plates. So if we have, for instance, we have the if we have these two plates that have some sort of insulation in between, right, then we shall have charges deposited on both of these two plates. So there will be equal and opposite charges deposited on these two plates. Now because we have a very high resistance insulation between them, these charges, this plus and minus, can never recombine. So the charge which is stored on this capacitor is given by very famous equation Qt is equal to CVT, where this where the charge stored here depends on the voltage Vt which is applied here, while this C is the constant of proportionality and is known as the capacitance of that particular material. And this value C is the capacitance, given as C is equal to epsilon A over D, where A is the area of these plates, which are the conducting plates. D is the distance between these two plates, and the epsilon is the permittivity of the insulation material which is used. Remember that this insulation material is a very high resistance material. Normally impregnated paper, mica, ceramic, etc. are used between these two conducting elements. Now the current flow here follows the famous theory of physics, which is known as a displacement current. So you should go through the some basic books, undergrad books on physics, to understand the real behavior, how current actually flows through this particular capacitor. However, because of the insulation here, the theory of the simple theory do not is not much relevant here. So C is equal to epsilon A over E. Uh, Also we know that the current I is equal to, I is the time rate of change of the charges. Since current is the time rate of flow of the charges, so I is equal to dqt by dt, and this implies that I is equal to C dv of t by dt. And this equation provides us the useful information about the capacitor. The first thing here is that for the current through a capacitor, there should be time rate of change of voltage, time rate of change of the voltage. This means that for all the DC circuits, where the voltage is fixed or a voltage is constant, that is, this dV by dt is equal to 0, then the capacitor is an open circuit. And that is perhaps the reason that the circuit symbol of capacitor has an open circuit in between these two plates. So this is the circuit symbol of the capacitance. This is the symbol. This open circuit actually relates with this particular thing, that capacitor is an open circuit whenever a DC supply is given. Also, the unit is farad, only known as an F. So a capacitance of 1 farad is a really very large value. So usually the capacitors come in the in couple of hundreds of microfarads, or perhaps sometimes in thousands of microfarads, and that is still considered a very large value. From this particular equation, that I is equal to IC of t is equal to C dV of t by dt, this equation reveals that the voltage across a capacitor cannot change instantaneously. Cannot change instantaneously, because that requires the similar logic that we require to have an infinite amount of current flowing through it, which is not a real world phenomena, because that again is associated with the infinite amount of power. If we integrate this particular equation, if we integrate this equation, then we get v of t is equal to 1 over c integral minus infinity to t naught I of t dt plus 1 over c integral t naught to t I of t into dt, where this particular portion is known as the initial condition of a given circuit. This is the initial condition of that given circuit, and that is that the voltage across instantaneous voltage across a capacitor depends not only on the present value, which is given by 1 over c integral t naught to t I of t dt, but also it depends on the previous voltage stored on the capacitors, right? So the information about the uh, previously stored voltage is very important, and this is the concept of the energy storage element, and that is why it is said that energy storage elements have memory within, and that memory makes the circuit dynamic in particular nature. So now you see that the involvement of these integration and the differential equations in the circuits containing the inductance and the capacitances makes the circuit more complex in solution in towards a solution compared to the static circuits where only the resistances were part of the network. If we move ahead with the energy storage, then based on the similar expression, we have energy stored in a given capacitor is given by half CV square, and that again comes with the concept of the same thing, that we first want to have, we will first establish the power which is associated with the capacitor, and that is equal to CV dV of t by dt, and thereafter we integrated it over time to get this value equal to half CV square. This energy is actually stored in the electric field. Now if we have some capacitors connected in series, we have this capacitor 1, this is capacitor number 2, and this is capacitor number 3. Let us say this is C1, this is C2, and this is C3. Here we have plus 1 as VC1, this is plus 1 as VC2, and this is plus 1 as VC3. So Vs is equal to V1 VC1 plus VC2 plus VC3, and because we have seen that the voltage across a capacitor contains the integral part as well, so the equivalent capacitance will be equal to 1 over C1 plus C2 plus 1 over C3, and then there will be the rest of the equation. However, we are only interested in this particular part, which gives us that the C equivalent is equal to 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So for a two capacitor network, C equivalent is equal to C1 C2 divided by C1 plus C2, and this particular expression is exactly opposite to that of the inductor and the resistances. Remember that this expression was for the parallel connected resistances and the inductances. The capacitor, if it is connected in series, its equivalent value is obtained in the same way we get the equivalent value of parallel connected inductances and the resistances. If they are connected in parallel, for example, we have these capacitances here. So let us say we have three capacitances here. This is C1, this is C2, and this is C3. And if this is IS, then we have this is IC1, this is IC2, and this is IC3. Then IS is a sum of this IC1 plus IC2 plus IC3, and this gives us C dV by dV1 by dt, because this V is same for all these four devices, including the three capacitors and this current source. So we have this C1 plus C2 plus C2 dV by dt plus C3 dV by dt, and this gives me C equivalent, which is the sum of C1 plus C2 plus C3. Notice here that we have a different situation here for this capacitor, because the capacitor is adding in a similar way like we added the resistances connected in series. But this is really a very interesting phenomenon, because for most of the time, if some capacitance of higher value is required, because the size of the capacitance also matters a lot, so it is sometimes recommended to have two 500 microfarad capacitances in parallel to obtain a 1000 microfarad capacitance, provided that the voltage rating is fulfilled. That actually reduces the financial burden which is associated with the capacitors as well. Unlike the inductances, the capacitors are commercially off the shelf available devices, and for various different values, the capacitances are available in the market that can be furnished when as and when required in a given circuit. We do not have to design the capacitance, just like we discussed that for any given application, the inductor may not be available in a given market, and therefore the first the core is purchased, and then based on the designing of that particular application, the shape of the core is first selected, and thereafter we wound the coil on that particular core to develop a given inductor. But this is not the case for the capacitors. Capacitors are easily available in the market, and they can be used in the circuit just like a plug and play device. Let us have a summary of what we have learned so far. Let us say we have inductor here and we have a capacitor here. So a linear inductor has flux current relation linear, whereas for a capacitor the charge voltage relation is linear. Remember that both the linear capacitor and linear inductor has nothing to do with the voltage and the current relationship, just like the resistances we have seen earlier. So for inductor, the linear inductor has a flux current relationship linear, and for the capacitor the charge voltage relation should be linear. For a DC circuit, L is inductance is actually a short circuit, whereas for a capacitor, for a DC circuit, the inductance L, the capacitance C is an open circuit, right? The third thing here is that the inductor stores energy in the form of magnetic field, whereas the capacitor stores energy in the form of an electric field. Also, inductor opposes sudden change in current, whereas the capacitor opposes sudden change in sudden change in sudden change in voltage, right? An inductor can store energy if the voltage across it is 0. Whereas a capacitor store energy if the current through it is 0. Through it is 0, right?
So I hope you have all enjoyed this particular lecture. Feel free to comment in the comment section if you have any questions so that we can cover them up in the next lecture. Thank you very much.